Hello and welcome to our 12th clinic. So today we're going to look at the definition of a vector space. So we're really going to be looking at prove 3 vector spaces and then this set of properties right here. So we're told that V is a vector space and we're asked to show that K times U minus V is equal to K times U minus K times V for every vector UV in our vector space and every constant K. We're also asked to show that U plus U is equal to 2 times U for every vector U in our vector space. All right. So proving part A. And so we start with K times U minus V. Well, by definition, this would be K plus negative 1 times V. Right? Because it's a vector space, we can distribute across addition. So we get K times U plus K times negative 1 times V. Again, because it's a vector space, we can combine the constants. And then by definition, that is KU minus KV, right? So proving letter B. Right, U plus U, that is obviously 1U plus 1U. Because this is a vector space, we can factor a U out. Right, because scalar multiplication distributes across scalar addition, which gives us 2U as desired. And so here we're told that V is R2 under addition, scalar multiplication as defined. All right, so let's move this down the line. There we go. So AB plus CD will be A plus C, B plus D. All right, and then scalar multiplication, K times AB is KA and then 0. Right, so we're going to show that V satisfies all of the axioms of a vector space except for the 10th and final one. All right, so first axiom. We want to show that it is closed under the definition of addition. So we take A, B, and CD to be elements of R2. Right? This means obviously A, B, C, and D are in the real numbers, so they're all real numbers. Well, that of course means that A plus C is a real number, and so is B plus D, right? If you add 2 real numbers together, you get a real number. But then by definition of R2, that would mean that A plus C and B plus D are in R2. Which would mean, of course, that AB plus CD is in R2, right? Because that's the definition of addition. So we've shown it's closed under vector addition. I don't know why I drew that. Second axiom is the commutativity of addition. Right, so add two elements. By definition, that. Right, but A, B, C, D are all real numbers, right? And we know that addition of real numbers is commutative. So A plus C is C plus A. B plus D is D plus B. And then by definition of addition, that is CD plus AB, right? So addition is commutative. Third axiom, we have to show associativity, right? So that first grouping winds up being A plus C, B plus D. Then we get plus EF. Which becomes this. Right, but again, all of these elements, right, are real numbers. And we know that addition of real numbers itself is associative. So A plus C plus E is the same as A plus C plus E, right? B plus D plus F is the same as B plus D plus F. Right, now we just work in reverse to break it back down. And we've now proven associativity. Fourth axiom is the existence of an additive identity. Right, so we have to say A plus B equals, A plus B plus some additive identity. What do I want to call it? I'm going to call it the zero vector. Has to equal A plus B, right? So we have to show that such a zero vector exists. Right, well, this is true if and only if A plus, call it 0 sub x, B plus, call it 0 sub y, equals AB. Right, and this would be true if and only if A plus 0 sub x is A and B plus 0 sub y is B, right? which is true if and only if 0 sub x equals 0, and so does 0 sub y, right? Because we're dealing with real numbers, and 0 is the additive identity for real numbers. So our additive identity is just 0, 0. Fifth axiom. We have to show that there exists an additive inverse. All right, so I'm just going to call it AB inverse, right? So we have to show that such an inverse exists, so that AB plus AB inverse is the additive identity. Well, this would be true if and only if A plus, let's call it A inverse, and then B plus, let's call it B inverse, is 0, 0, which would be true if and only if A plus A inverse is 0 and B plus B inverse is 0, which is true if and only if A inverse is negative A and B inverse is negative B. Again, because A and B are real numbers. All right, so our additive inverse would be negative A, negative B, right? So we have an additive inverse. So axiom 5 has now been proven. The sixth axiom. Closure under scalar multiplication. So we take an element in our vector space, pick any arbitrary constant, let's call it K. So this means that now all of our elements, A, B, K, are real numbers. This means that K times A is a real number. Right, which means that KA 0 is in R2, right? Because 0 is clearly a real number. We know that KA is a real number because if you take a real number, multiply it by a real number, you get a real number. So of course, that is the definition of K times AB. So we do have closure under scalar multiplication. The seventh axiom is distribution across vector addition. Right, so perform the addition first. We're going to get A plus C, not D, B plus D. Right, by definition of scalar addition, or not scalar addition, scalar multiplication, this is K times A plus C comma 0. We're dealing with real numbers. That's KA plus KC. And then I'm just going to write 0 plus 0. Well, that would be this, right? KA0 plus KC0, which is the definition right of K times AB, right, and then plus K times CD. Seventh axiom is satisfied. The eighth axiom is distribution across scalar addition, right? In other words, two scalars K plus M times AB, we want to show that's K AB, right? And then plus M AB. So the definition of scalar implication here, we're going to get the scalar K plus M times A and then 0. Since we're dealing with all real numbers, this is K times A plus M times A, and then we can write 0 as 0 plus 0. This can be split up as KA0 plus MA0, which of course is the definition of K times AB, right? And then plus M times AB. So the eighth axiom is satisfied. Ninth is the order in which you do the multiplication does not matter. Right? In other words, we look at this, Km times AB, right? This is the same as K times M times AB, right? So we're allowed to just multiply all of our scalars together. Why am I back? Oh, no, there we go. Right, so definition of scalar multiplication, we get Km A comma 0. Right, we're dealing with real numbers. Scalar multiplication of real numbers, right, is associative. So grouping doesn't matter. So this is the same as K times MA, right, and then 0, which would be K MA0 which would be K times M times AB. So the ninth axiom is satisfied. Right? Remember, that's what we wanted to do, right? We wanted to show that the first 9 axioms are satisfied, 10 isn't. But what's 10? Well, 10 states that the real number 1 is the multiplicative identity, right? So what we need is that 1 times AB equals AB. Well, by definition, this would be 1 times A and then 0, which is A0, which is not A times B. So the 10th axiom is not satisfied. So all the axioms except for number 10 are satisfied. That is what we wanted to prove, and so the proof is complete. Do that one or just skip it. we're going to say V is the vector space R infinity, right? So that's just the set of all infinitely ordered paired real numbers, right? So R2 is ordered pairs. R3 is ordered triples, right? Where each part of the ordered triple is a real number, so on and so forth. Addition is defined as you would expect, right? You just add each component together. Scalar multiplication, defined as you would expect. You just multiply each component by the scalar. We're going to show that this forms a vector space. Right, so what does that mean? Well, it means that we have to show that this set combined with the two operations satisfy all 10 of the axioms. So start with closure under addition. I'm going to stop calling it R infinity. I'm just going to call it V because I'm too lazy to write infinity all the time. So these two vectors being in V, right? This means A1, A2, dot, 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 B1, B2, dot, 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 right? So every A and every B are real numbers. Well, again, if you add real numbers together, the result is a real number. So then this ordered, let's call it infinity tuple, would be in V. Right, and so the sum of these two is in V, so we have closure. Number two was commutativity. Again, we're dealing with all real numbers, right? All of the A's are reals, all of the B's are reals. Since we know that addition of real numbers is commutative, we can write this. But that is the definition of the B plus the A, right? So there we go. Third axiom, we have to now show associativity of addition. Right, this will be A1 plus B1, A2 plus B2, so on and so forth, plus the C. Right, that'll give us this. We know that the addition of real numbers itself is associative. So how we group them doesn't matter. Right, so we're allowed to write that. We now deconstruct it. Right, so this is the A plus then B1 plus C1, B2 plus C2, so on and so forth, which is the A plus the grouping of the B plus the C. So we now have associativity. Fourth axiom, the existence of an identity, an additive identity. Well, I claim that the ordered infinity tuple of zeros is the additive identity, right? So let's go ahead and prove that claim. And we know what happens if we add a real number to zero. We just get that real number. So there's our additive identity, the infinity tuple of zeros. Fifth axiom is the existence of an additive, not additive identity, additive inverse. Right, well, I claim that if you just multiply the vector by -1, you get the additive inverse. And quick calculation shows that that claim is correct. So we have an additive inverse. 6 is closure under scalar multiplication. We're going to take the A to be in our vector space, some scalar R, or K rather, right? So that means all of the A's plus now this K are real numbers. I'm just going to write it this way. KAI is a real number for all I's. So I mean, this vector is in V. Right, so K times the A is a vector in V. We have closure under multiplication. 7. All right, we're almost there. So we have to show now that scalar multiplication distributes across vector addition. That'd be K times A1 plus B1, A2 plus B2, so on and so forth. Which by definition of the multiplication would be this. Now, since we're dealing with all real numbers, right, we know that multiplication distributes across regular addition. That's what we get. Which by definition of addition would give us, oops, would give us this. Right? And then by definition of multiplication, we get k times the A plus k times the B. So scalar multiplication distributes across vector addition. Now we have to show that scalar multiplication also distributes across regular addition. And so by definition of multiplication, this is what we get. Now we're dealing with strictly real numbers. Right, so we can distribute the A's across k plus m. Right, by definition of addition. We get that. And then by definition of multiplication, we get k times the A plus m times the A. So that has been proven, right? So scalar multiplication also distributes across regular addition. Then we have to show essentially associativity of scalar multiplication. By definition, we get this. We're dealing with real numbers, right? And multiplication of real numbers itself is associative. So we can group it however we want. So why not group it that way? Now, by definition, we have k times that vector, right? And again, by definition, we get k times now m times the A vector as desired. Last one. We have to show that 1 is the multiplicative identity. So 1 times A1, A2, so on and so forth. Right, that'll be 1 times A1, 1 times A2, right, so on and so forth. Since these A's are real numbers, one times the real number is the real number. So we get the original vector back. All 10 axioms thus are satisfied. And we can say that this set, R infinity, under the two operations, addition and multiplication as defined, is a vector space. Right? Or it's also known as a linear space. And we got one more. So here we're being told that U and W are vector spaces. And we're going to say V is a set of all ordered pairs UW, such that U is in U and W is in W, right? Which, by the way, we can also say that V is the Cartesian product of U and W, right? With addition and scalar multiplication defined as the standard addition and scalar multiplication, right? So you add components together and you just multiply each component by the scalar. We're going to show that this defines a vector space. Right now, this vector space is called the external direct product of U and W. The first thing we have to do is show that it is closed under addition. So we're going to say UW is in V. I'm sorry, UW, and let's call it U prime, W prime, are both in V. This means that U and U prime would be in U, right? W and W prime would be in W. Replace that with an and. Well, since U and W are vector spaces, right? U plus U prime would be in U. However, that addition is defined. W plus W prime would be in W, right? Again, however, that addition happens to be defined. Which means that that would be in V. Right, and so that sum is in V. So we do have closure under addition. Okay. So we now want to show that addition is commutative. And so by definition, this is U plus U prime, W plus W prime. Right? But U is a vector space, right? So addition in U is commutative. So we can write this as U prime plus U. Okay. And then again, W is a vector space, so addition is commutative in W, right? So W plus W prime is the same as W prime plus W. Angry kid, so I apologize for that. And no, U prime is not the derivative. I'm just using U prime as a different variable, right? To show that it's different from the original U, but I still kind of want it to look like U, so I can say it's in the vector space U. Right? So by definition, this would be U prime, W prime plus UW. So addition is commutative, right? We now want to show associativity, right? So we're going to take UW plus U prime W prime plus, let's call it U double prime and W double prime. So we get U plus U prime, W plus W prime, right? And then all that'll be plus U double prime, W double prime. And by definition, we'll have U plus U prime, then plus U double prime, W plus W prime, and then plus W double prime. Well, again, we know that U and W are vector spaces, right? So addition in U is associative, addition in W is associative. So how we group these additions does not matter. Right now, just decompose it. So we get, this is UW plus U prime plus U double prime, W prime plus W double prime, which would be UW plus then U prime W prime plus U double prime W double prime. So there we go. We have associativity. So now we have to show that there is an additive identity. Well, U and W are vector spaces, right? So because U is a vector space, I know there exists some vector, call it 0 sub U. Such that U plus 0 sub U is U itself, right? So U has to have an additive identity. Likewise, there has to exist an additive identity in W, right? Because W is a vector space. Well, then why don't we just take our additive identity in V to be zero U comma 0 W, right? So the additive identity of U comma the additive identity of W, right? Doing this, notice what we get. We get U plus 0 U, which is just U, and then W plus 0 W, which is just W. So that is our additive inverse. I'm sorry, our additive identity. Additive inverse. Well, again, U is a vector space, so there has to exist some negative U in U such that U plus negative U is the additive identity in U, right? And then likewise for W. So again, why not just take the additive inverse of V to be that ordered pair? Well, that then means if we add them together, right, we'll get u plus negative u, comma, w plus negative w. Clearly, we get the additive identity. That takes care of the addition axioms, right? So now we have to deal with the multiplication axioms. First one, again, is closure. So we're going to say we're going to take UW in V and K being some real number. Well, then we have to have U being in U, right? And W being in W. But this would mean that KU is in U, right? And KW is in W, right? Because U and W are vector spaces. So we know that they have to be closed under scalar multiplication. That would then mean, by definition, right, that KU, KW has to be in V, right? Because that's how we defined V. Right, well, then that would mean that K times UW is in V. So we have closure under multiplication. So now we have to do distribution across vector addition, right? So we have to do K times UW plus U prime W prime. This would be K times U plus U prime, W plus W prime. By definition would be this. But U is a vector space. So we can write that first component, right, as KU plus KU prime. W is also a vector space. So we know that that's going to distribute. Well, this is the definition of KU KW plus KU prime KW prime, which would be the definition of K times UW plus K times U prime W prime. So that axiom has now been satisfied. Right, so number 8, we have to show that it now also distributes across regular addition. Right, so by definition, we're going to have this. But U is a vector space. So the first component distributes. But W is a vector space. So the second component distributes. Well, that would be the definition of this, right? KU, KW plus MU, MW, right? Which is the definition of K times UW plus M times UW, which is what we wanted, right? So this axiom is satisfied. Ninth axiom is associativity. We're going to take K times M, multiply that by UW. By definition, We get that, right? But U is a vector space, right? So it's associative in U. So we can write this, K times MU. But W is a vector space. So we know that associativity holds in W. So we can write that as K times MW. By definition, that is K times MU MW, which by definition is K times M times UW, which is what we wanted. So we got one final axiom, right? 1 has to be the multiplicative identity. So 1 times UW has to be UW. By definition, this is 1 times U and then 1 times W. But U is a vector space. So 1 is the multiplicative identity in U. So 1 times U is U. But W is a vector space, meaning that 1 is the multiplicative identity in W. So 1 times W is W. Hence, 1 is the multiplicative identity in V. So the 10 axioms have been satisfied. There are set V with the 2 defined operations, addition and subtraction, forms a vector space. As desired. Right? Okay. So that is going to do it for today's clinic. The next clinic is going to cover subspaces, right? So thank you all for attending. Thank you all for watching. I will see everyone in the next clinic.